Let me share my. So yeah, coming to what we did in the last session, we talked about some physics-inspired algorithms, also physics-inspired neural networks. So what we talked about was one particular algorithm known as GSA, which is gravitational search algorithm. So this algorithm works on the principle of Newton's law of gravitation, and we also formulated this algorithm, how it works and everything. Uh, so do any of you have any questions regarding this algorithm? We also talked about various kind of like optimization problems. Uh, so we talked about various kinds of different optimization problems as well as what is heuristic optimization, and one of the main this was the attempt to uh, get optimal solutions and not the global minimum or maximum. This was the main goal of physics inspired algorithm rather than finding the global optimum. So, and also we talked about physics inspired neural networks. So what are physics-inspired neural networks? They are, as I said, similar to neural networks, but they also have a factor in them which make the neural network learn the physics of any whatever we are learning. So it usually had if you have a equation which is a differential equation is equal to zero, you add this particular term to your loss function. So this was about yesterday's, not yesterday, the last class. So today we'll be taking a look at few more algorithms which are again physics inspired, as well as we'll also be uh, delving a little bit into quantum computing, which is again a type of computing that is inspired from physics. So that will be what we'll be covering today. So first of all, I'll start off with another algorithm that is called colliding bodies optimization. So I assume you know what happens when two bodies collide. So say there is a block and there is one more block. So this has mass m1 and this has mass m2. So and this has velocity v1 and this is velocity v2. So when they collide, what happens? Collision detection optimization. I don't know what is collision detection optimization, so I'm not sure about that. But I don't think it is similar to that. This is again a heuristic optimization where collision of bodies is taken into account. Uh, so yeah, what happens when two bodies collide? Anyone? They release energy. I mean, yeah, in the non-ideal case, of course, they do. They lose some of the energy. New mass is formed. No, 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 no. Don't talk about uh, uh whatever, like just simple Newtonian mechanics where two bodies are, yeah, momentum is conserved. That's the main thing. So this is basically conservation of momentum, which is m1 e1 plus m2 v2 is equal to m1 v1 dash plus m2 v2 dash. So this is what will happen. What about the kinetic energy? Anyone? Yeah. So kinetic energy won't always be conserved. So what will happen is we can write it as m1 v1 square plus m2 v2 square is equal to 1 v1 square. So yeah, this is a cube. Uh, so you can see that yeah, total energy should be conserved. So what we are writing is the initial kinetic energy is equal to the kinetic energy afterwards of the two particles. And this Q is the loss in kinetic energy. So this is what it will be. Now, if we are to find the relation between V1 dash, V2 dash, V1 and V2, uh, we can do it. But I'll just write the equations directly, which is so V1 dash will be something like M1 minus Yes. Should be. Mhm. So here, uh, right. So here, what is epsilon? Whatever I have written. Yes, sir. Anyone? Epsilon is not the total energy. Yeah, it's the coefficient of restitution. So what is coefficient of restitution? I'll come to it. I'll just write this down. So these will be the not the factor by which the mass has changed. The sum of the ratio of how velocity has changed. Uh, so this will be uh, V2 dash minus V1 dash divided by V2 minus V1. So what will this coefficient of restitution be for an object which is not for an object, for a collision which is perfectly elastic? So and for inelastic collision, it will be zero, and Q will not be. It will be a positive. Okay. But what does this have to do with optimization? Like I'm just writing some physics. Yeah, it's zero for less than perfectly inelastic collisions. Uh, but what does this have to do with uh, optimization problems? Like how do you formulate something so that you optimize something? Optimization could be anything. It might be uh, like I said yesterday, there are quite a lot of optimization problems. Now, how do you have something using this thing to optimize something. So that is how I'll tell you how colliding bodies optimization is formulated. So basically what we consider is, so okay, total and velocities of body. So this colliding bodies optimization, uh, this is based on 1D collision. So it's just one-dimensional collision of objects where each solution in the search space is considered to be a body. Okay. So that is the basic idea behind this. Now, again, we have say n number of bodies. N agents. We again divide them into stationary and moving objects. And so basically the idea is that we improve the positions of moving objects and push stationary objects to better position. So we define it so that the stationary objects, they're already the ones which are having a better fit fitness value. So basically they are closer to a optimal value than the moving object. So what happens is I had talked about exploration and exploitation. So it is somewhat similar to that. Uh, moving objects which have lesser mass, they hit stationary objects which have more mass. So basically you have your objects which are uh, having more mass move a little bit in the direction where there is more optimal. Uh, is the exploration and exploitation part clear? Okay. So what are the uh, how is this algorithm implemented? So first thing is a random initialization is done. So what it means is you just have your search space, which can be this plane. You randomly initialize some uh, agents somewhere and then calculate the value, which is the fitness value of, which is also the mass. So mass for each object is defined this way. So this is just a normalization factor that comes in. Uh, 1 by fitness by uh, summation 1 by fitness. So this will be the mass. So as you can see, the one having higher fitness here will have a lower mass, which is for uh, so this term can also be basically fit as well. So if you want more fitness value, which is if you want a maximization problem. If you want a maximization problem, then 1 by fitness becomes fitness. So now what you do is uh, the objective function you have, and you do a ascending order of this objective function. Okay. And then the first half, oh, fitness is just the value of your objective function only. It's nothing else. Like if I say like say you want to maximize something, right? Uh, your yeah, your fitness would be defined as the objective function, and when you reach the maximum value, you will have the max fitness. But while you have the objective functions, I think it's better to say here as uh, put this as objective function instead of fitness. But yeah, so fitness is basically how close you are to your like optimal value. You can't really get that, but it's just saying how better your value is. Uh, yeah, it should be fitness by summation of fitness because uh, higher the fitness, which means it's closer to. It again depends on how the if it is just the optimization problem. Sometimes there are also other measures to measure fitness, but if it's just the optimization value, then as your fitness increases, your mass increases. If you see in the if you do it fit by summation fit, you can see that as you increase your mass, increase your objective function, your mass also increases, which is what we want. So it will be fitness divided by summation of fitness. Yeah. So you have two halves now. Uh, so you have 1 to n by 2 here and n by 2 plus 1 to n here. So what do you do with this is you again make half of it stationary and half of it moving. So this is stationary and this is moving, depending on the problem your so depending on the optimization problem you have at hand. So is everything clear until here? Any questions? So now again, based on some, so what we do is here, 1 is paired up with n by 2 plus 1 and so on. So you get the idea that this is I and this is n by I minus n by 2. Okay. And I ranges from n by 2 plus 1 to n. So you pair it up in this way, and then you calculate their velocities as well as positions. So I'll just write one velocity to be calculated, which will be mi minus epsilon mi minus n by 2. So your epsilon is your coefficient of restitution times V1 by mi, uh, basically at the both two masses. So this will be your new velocity. And similarly, you will get new velocity as well as based on velocity positions. And using this, you continue this process until you either reach maximum number of iterations that you have specified or get a decently good value. So this is basically the idea behind colliding bodies optimization. Now there is also one more thing, which is epsilon is defined as 1 minus eta max. So what this is your epsilon helps in your exploration and exploitation, where if the epsilon value is 1, there will be exploration. While if your epsilon value is 0, which is perfectly inelastic collision, then there will be more exploitation. So that is why we are keeping it such that you are uh, maximizing exploration at first and maximizing exploitation afterwards. So this is about this thing. Uh, Another algorithm that is not exactly inspired from physics, but then again has some physics aspects to it. It is harmony search. So two algorithms I have, which I won't be explaining much in detail. Like I just go through them and then we'll move ahead with some other stuff. So harmony search. So harmony search. How many of you here like play some musical instruments or something? Yeah. For those who play musical instruments and everything, you know that getting the pitch right and getting your uh, uh, you will have to be actually like work on setting the uh, get the aesthetic quality, like it should sound good, right? That's the main idea behind playing any sort of music. So pitch is basically determined by frequency, and a musician will always try to uh, get the best pitch out of his instrument. So how is a optimization algorithm inspired from music? So I just explain this in terms of a problem itself. Say you have a optimization function that goes like x minus 1 square plus y minus 3 square plus 3. Let's keep it at z minus 2 square plus 1, whatever. So now, uh, this will be having some set of solutions, but you have to minimize this. You can just look at the uh, this is a very easy problem. You can just look at the function and say the minima comes at 1, 3, comma 2, 1, comma 3, comma 2. But that won't be the case for higher dimensional objects, which are not so simple as this. So what happens is we have something called as a to get the actual term. Uh, you have harmony matrix or something like that, which is like gem. So basically, you initialize with something. Say the initialization is like it's a set of a matrix like it is 2, 3, 5, uh, 5, 3, 1, and 1, 4, 3. Say this is your harmony matrix. Now what you do, this is a random initialization. You have this, you plug it into the values and you get some values here. So F1, F2, and F3. And now again from this particular set, you take one more set of values. This is just a very simple example that I'm giving, but it can be multiple dimensions as well. Say you choose one from here. You choose one from this set for X. For Y, you choose 4. And for Z, you choose 1 again. So you get one more F4 value, one more optimization function. Now you compare the how good this, not from a aesthetic standpoint, but from an optimization standpoint, how good this value is. So if this value is better than this value, which is F3, uh, then you replace F4 this. So the matrix is replaced by this. And you continue doing this until you get a good enough, the best pitch, which is the best result out here. So this is just the uh, very basics of harmony search. I'm not gonna cover it much in detail. Now, one more very interesting algorithm is that everybody knows about the Big Bang, right? Yeah. So what is Big Bang? The Big Bang theory. It's not the show, by the way. Not the show where one Sheldon Cooper is giving some lecture on physics or whatever. This is, yeah, it's the beginning of space and time. Uh, yeah. So basically, what the theory is that you have like a very dense, in the beginning, universe was very dense with matter and everything, and high temperature as well, and then it started expanding. Yeah, the explosion. So uh, currently, what is happening is universe is expanding right now, and that is Big Bang. But what is Big Crunch? Does anyone of you know? It's again, Big Crunch is a very hypothetical situation. It's hypothetical theory. It's not something that is proved or anything. But yeah, yeah, I think you meant contracting there. But yeah, that is what it is. Yeah, it is the opposite of Big Bang. It's said that when the universe ends, what will happen is not exactly when the universe ends, but before that, we'll reach a point where universe, instead of expanding like that, like it is doing now, it will start contracting because gravitational attraction will exceed whatever other expanding forces are there. So in the end, what happens is, so you have an entire what do I say? Yeah. So you have some whatever galaxies or whatever, and they'll all collapse into one single point. And there are also theories that this will lead to another Big Bang and then so and so, and this will be a cycle. Of course, we won't be alive to witness a small part of this cycle also. Uh, the value of Hubble constant. Yeah, I mean, it's a very hypothetical concept, so I don't know exactly how that works with all this Hubble constant and everything. And I don't think majorly this has been proved, but it has at least inspired an algorithm to uh, go about. So, what is this algorithm specifically? Which is the Big Bang Big Crunch algorithm. So, what happens is you initialize points on your search space with random points again. So all these algorithms, one thing if you have seen, the common thing is that you have uh, you have random initialization. So this random initialization is compared to Big Bang, where like you have some sort of not exactly expansion, but some sort of this is randomness exists. And then what you do is you consider either the one with the largest mass or you consider the center of mass. So if you have, say, some three objects, this this red dot will be our center of mass. So what happens is basically when you have this, you say that this will all converge to the center of mass. But again, this there is no possibility that it gives the global optimum every time. It again might not give a proper optimum solution itself. So what you do is you repeat this process of Big Bang and Big Crunch for certain number of iterations so that in the end you get something that is what do I say? A optimum solution. Not exactly global optimum, but again, not very bad minimas. So again, here you have the center of mass. I think center of mass calculation here, how they have presented is you have mass of the object divided by the stiffness summation, and you have 1 by. So Fi. Fi is again fitness, which is determining based on what we want to optimize, how close, like how good that particular value is. So once this is done, uh, again, a new, what do I, yeah, how do you create a big bang from this again? Like if you again randomize everything, it will not be very, it will just be a random search. It won't be a algorithm as such. It will be just searching through space for like, okay, I'll go to this space, I'll throw a dart at this point. Let's see what the population. So what they do is instead of doing this, but a new Big Bang is created around the center of mass or the best fit individual. And then again, this uh, process is repeated until you get a very nice, I mean, until how many ever uh, iterations that you have put in. So, yeah, any questions about both of these algorithms? So I haven't explained about harmony search and also Big Bang Big Crunch algorithm in very detail. If you are interested, you can go through it. There are also a lot more algorithms. After this, Toshit will take up simulated annealing, which is a very famous algorithm and something that is widely used and has been used for a lot of stuff. Yeah, if you don't have any questions, we can move on to simulated annealing. Okay, I'll stop sharing my screen. I'll send these notes. Yeah, Toshit, you can continue.
Uh, oh yeah, so hello, is my screen visible there?
Yes, your screen is visible.
Uh, okay, yeah. So hello everyone, I'm Toshit and I'll be going over the topics of traveling salesman problem and then how to solve the problem using simulated annealing. Uh, yeah. So starting off, before telling you what traveling salesman problem is, I'll start by saying what a combinational optimization is. I mean, you might have learned optimization methods in our class 12th, like linear programming and all. So combinational optimization is a subfield of mathematical optimization where a certain set of discrete solutions exist and a particular solution among them is the best. Traveling salesman problem is a type of combinational optimization problem. Well, what is basically in traveling salesman problem? So let's say an Amazon delivery guy will have all of his what all stuff he needs to deliver. He'll have it in his warehouse. Now he has to pick various. He has to deliver these goods in various locations around the city. Well, he might obviously want to reduce the travel distance and the travel time. that it takes to deliver all the products to their location, and then as well as come back to his warehouse. He would want to pick the most efficient path, and hopes that he could like be able to do this always. Like for any, like let's say the locations are changed, he should still be able to follow. Should still be able to decide a new path, so which is efficient for him to deliver the products. Okay, so reading the problem statement of traveling salesman problem. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the original city? Okay, yeah. And also, currently, I'm only considering symmetric traveling salesman problem. What this means is, let's say from going from city A to city B takes whatever amount of time it takes to go from city A to city B is the same amount of time it takes to go from city B to city A. And also the distances is same both ways. Yeah, and also traveling salesman problem has several applications, such as in the planning, logistics, and manufacturing of microchips. And slightly modified, it appears as a sub-problem in many areas, such as DNA sequencing. Yeah, so I'll move on to like actually solving traveling salesman problem. Well, after you have decided on what all locations will be delivering, let's say you have n locations to deliver your products. Now let us try the brute force approach, wherein you have n cities. So you take different tours traveling to all the n cities and coming back to your original location. Uh, the total number of possible paths in this case is n factorial, and it is n factorial. And now what you'll have to do is calculate the total distance it takes in each of these tours, and then find the shortest among them. Well, this is simple if let's say n is like something as 10. So then 10 factorial computation is doable. But what if you have 100 locations to visit, but then your computer like the computation would take years to calculate this. So we'd obviously yeah, so we would obviously look at some better, efficient and more feasible solutions than actually going directly for brute force method. Well, there are many algorithms. I'll be talking about. Firstly, I'll be talking about simulated annealing, which is physics inspired, based on the physical process of annealing. Okay. Yeah, I'll come on to that. And simulated annealing is a meta heuristic algorithm, or like a probabilistic algorithm, which you have seen in part one of our session. Okay, yeah. So I'll come to what simulated annealing is. Like what annealing, it simulates the annealing process. What annealing is where a metal is heated to a high temperature quickly and then gradually cooled. So what happens is initially at a higher temperature, the atoms have more energy and are moving around with high velocity. As the temperature cools down, they quickly settle in and form a like and quickly settle orderly. Yeah. Yeah, and I'll explain this, Jeff. Over here, we like all these dots are actually the cities or locations what you would like to travel. This is like the when the GIF started, that was your initial touring path. What the algorithm then does is it tries to find out the minimum touring distance, which you can see now. So I mean, I'll have written a program to which actually simulates this, and we'll go through that. Simulated annealing, as I said, is a meta-heuristic algorithm. Yeah, so I mean the physical process of annealing like starts with metal being at a higher temperature. Okay, I've gone through this. Okay, yeah. So similar to annealing process, simulated annealing starts with a high energy state, which is our initial solution, which is not the best solution, as you can see through over here, uh, waiting for the initial solution. Yeah, so this is not the best travel distance, obviously. So our program starts with a high energy state, which is our initial solution. And then the program gradually lowers the temperature, which is a parameter that we control in the program. And then as the temperature gradually reduces, the energy of the program, or let's say the optimum solution, is reached. Energy of the program is reduced and we reach the optimum solution. Yeah, and simulated annealing has been successfully applied to a wide range of optimization problems such as TSP, traveling salesman problem, protein folding, graph partitioning, and job shop scheduling, etc. So, okay, we'll actually now move on to implementing simulated annealing. So, yeah, simulated annealing starts with an initial solution. What this means is we select an initial tour that our delivery person has to take. He can select this tour at random, maybe something which is, let's say he goes to whatever is nearest to him first. Okay. And then we iteratively improve the current solution by randomly perturbing it and accepting the perturbation with a certain probability. What this means is, let's say in one case you are in Delhi and you would like to visit Mumbai and Chennai. Well, you could go from Delhi to Mumbai, then Chennai, then back to Delhi, or you could go from Delhi to Chennai, Mumbai, and then back to Delhi. So in this way, you have like changed your touring path. But in this case, the tour distance is the same in both the cases. But if you have many such locations that you would like to travel, you would randomly swap your path to go from one city to like you would randomly swap the location of two cities or so that your path is updated. You'll try to see if you're getting a good solution out of that. Okay. What does it mean that we'll accept the solution with a certain probability? I'll come to this point later. And yeah, and the probability of accepting a versus solution is initially high and gradually decreases as the number of iterations increases. Okay, I'll come to these points as I go through the steps of actually implementing simulated anything. Okay, so actually we start off first by defining the problem. This means we define an objective function. Or like we define an objective function with to either maximize or minimize our solution. What in our case, what the objective function takes is our touring path. It takes the touring path and gives out the touring distance or the travel distance that the delivery salesman has to take. Yeah, so once the objective function is decided, we'll set an initial temperature and initial candidate solution. I'll come to initial temperature again later. And in what the initial candidate solution is basically our traveling salesman, he decides a path at random, like some path, so that you can get started with it with something at least. Okay, so then we'll go to step two. Well, step two is basically perturbation function. I mean, this is the same as swapping cities in our path. What like we'll do this randomly. We'll randomly select two cities to swap. So let's say if you're going from city A to B and then from B to C, you would swap B and C such that from city A you would go to city C, then from city C you would go to city B and then move on. So that is what the use of perturbation function is. And okay, yeah. So I'll move to the acceptation criterion and I'll discuss the basic algorithm here. So the acceptance criterion of simulated annealing comes from statistical mechanics. It is based on the Boltzmann probability distribution. Uh, I mean, yeah, the energy of the state is proportional to E raised to power I mean, okay, sorry, E raised to power minus E by KT, where K is the Boltzmann constant and T is the temperature. Okay, I'll explain this pseudocode that I have here, and I'll be using this graph as well. So what you initially do is pass like obviously the salesman has picked an initial candidate. You'll pass that initial candidate to this objective function. This objective function gives us the current solution. Now you update your touring path and then pass it back again to the objective function, which then gives us the new solution, which is the traveling distance of the new touring path that we have. Well, there might be two cases. Either the traveling distance of the new solution is lesser than the current solution. In this case, we accept the solution. Well, if it is not lesser than, or like in this case, you're trying to minimize. So if it is not lesser than the current solution, then we go on to the else block. Over here, I'm defining a variable called probability, which is equal to E raised to power minus the current temperature divided by initial temperature. Okay, I'll come to this. So in the annealing process, the temperature gradually cools down from a higher temperature to a lower temperature. What this means is in this the variable probability, as the current temperature keeps on cooling, it gets lesser and lesser than the initial temperature. Looking at this graph, let's say that the initial temperature is 100, and over here x keeps on decreasing, and as basically this means that x is approaching 0. So over here, as x approaches 0, the variable probability attains a value closer and closer to 1. Uh, okay, yeah. And then like probability is assigned this value at each iteration. And then we have a function called random, which generates a random number between 0 and 1. And what we do is if we generate this random number, if this random number is greater than what the value of probability is currently, then we accept the solution, or else we reject the solution. I'll come to why we accept the solution in the next slide. I'll explain this. Okay. 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 One more thing. How do you decide how many times do you want to update your path, and then how do you decide how many times to run this code? This block of code. I mean, you'll change your path and you'll look for a good solution than your current path. But then how are you sure that, I mean, how do you decide how many times do you want to run this? So in that case, we come to temperature scheduling. So what temperature scheduling is basically, obviously at the start, the metal is heated to a higher temperature. That is, we define a variable called Tmax, which represent our higher temperature. And then we reduce the temperature at every iteration by, let's say, 5%. And we keep reducing it till the current temperature reaches T minimum, which we ourselves set. Okay. What this temperature scheduling is like, I mean, analogous to what annealing is basically. At a higher temperature, the atoms have more velocity. Okay, wait, I'll talk about this in this way. So our objective function may have multiple minimas, and among them, one might be a global minima. So what happens is our program, it at a higher temperature, let's say it goes into some minima which is not a global minima. Like somehow it randomly when the path updates, it goes into a minima which is not a global minima. And then as the temperature is high, let's say you get a worse solution than what current, like the present place where you are, which is the minima. Let's say you get a worse solution than that. As the temperature is still high, coming back to this thing, as the temperature in the current temperature is still high, probability will have a value which is lesser. And this means the prob like that, I mean, yeah, so the probability that we accept the solution increases as probability is I mean, not close to one. It is it is lower. Okay, it is lower at a higher temperature. So probability of accepting a Bose solution increases. What this means is even if you are in a, let's say, local minima, and if the program randomly is able to get a Bose solution, then it means you're able to escape out of the local minima, and then you may be able to look at other minimas or end up in a global minima. Okay, so okay, I'll stop this here, and I have a program simulating this. But before I start on that, if you have any questions regarding this, you can ask.
There are some questions in the chat as well. Just-
Uh-huh. What is simulated annealing? Okay, annealing is a physical process of wherein you cool a metal. Sorry, I mean you heat a metal to a high temperature really fast, and then you gradually cool it down so that the atoms of the metal are given enough time to settle orderly. You do not rapidly cool it so that, I mean, you cool it gradually so that there are no stresses in the metal. So what simulated annealing is, we are trying to write a program which actually minimizes our objective function, whatever we have defined. We are trying to minimize it by like, I mean, having temperature and energy, or what should I say? We are trying to simulate the annealing process, but we are like, let's say our metal in this case is the objective function, which are trying to gradually cool and make it settle into a good, solution. Yeah. I mean, I think I have explained it briefly. Do you want me to explain it again, or? Okay, yeah, what perturbation means. Perturbation is another fancy word for update. It basically means, like in this case, let's say I'm in Delhi, I want to go to Mumbai, then Chennai, and then back to Delhi. So if I perturb this path, it basically means I change some touring path over here. Like, I'll from Delhi, I'll go to Chennai, Mumbai, and then back to Delhi. I have swapped the order of going to cities of, like, I'm order of going to Mumbai and Chennai. So that is what perturbation is. It basically means I'll randomly update my current touring path to see if I can get a better solution out of it. Okay, what does random parameter mean in the code? Okay, so random is for in Python, random is a built-in function. It just generates a random number between 0 and 1. So what I want to do is I'll randomly generate a number between 0 and 1, and I'll compare it with my variable probability. And I mean, you know the condition. If the randomly generated number is greater than probability, I'll accept it. I will accept the versus solution. Okay, I'll say that in this sense. Uh, okay, yeah, in this case, let's say our temperature has been reduced to, like, temperature is lower. So what this means is probability has value closer and closer to 1. Let's say currently it is 0.9. So now random generates a number between 0 and 1. So the probability of generating a number which is greater than 0.9, uh, that is it, which is the condition to accept the worst solution, is lower compared to the probability of generating a number between 0 and 0.9, which goes to the else case where a solution is rejected. So what this basically means is, as the temperature is reduced, the chances of accepting a versus solution are decreased. And at a higher temperature, you are able to explore more of the search space. By search space, I mean all the possible solutions. So that is the use of random over here. It is a built-in function in Python. Like, I'm not doing anything special over here. Um, yeah. Why do you want to disturb it? Okay. So what happens is, atoms are obviously at when when a metal is heated, atoms are constantly moving around. So we randomly perturb it to simulate this random movement of atoms. Um, well, at a higher temperature, like, the metal structure is not clearly, what should I say, is not organized properly, and atoms can move in and out of the crystal lattice. So that is why we have perturbation to, I mean, simulate atoms moving in and out, or like disturbing each other. There's no uniformity at a higher temperature is what we're trying to do. Yeah, any more questions? I'll move on to explaining the code, but like, if you still have any questions, you can feel free to, like, type it. Okay, fine. I'll move on to explaining the code, and as well, I'll share the code as well, so you can try it on your own. So, yeah. So, I mean, yeah, over here I have imported, like, various libraries. So currently I have a country which is 100 by 100, let's say kilometers for now. And the number of cities in this country are 10. I can change this over here, but for now I'll stick with 10. What I'm doing is I'm defining city as a dictionary where I'll store the city name as key, and the city coordinates as its value. And all of these functions I'll be using later on in my code, so I've just written it here. I'll Okay, yeah, this is where I would say I'll start the program. I've written two functions, which is random cities and default cities. So what random cities does is it randomly generates the coordinates of 10 cities, and then it connects them, like the connected cities is a list. It connects the cities to one another and then returns connected cities. What default cities does is I have defined. Okay, yeah. So what default city does is I have already stored the coordinates of, let's say, some number of cities in another function. When I call in default cities, whatever, whatever I have already stored, no new random cities are being generated. That is, that is, the coordinates of those cities are used further in the program. So when you're running this program, you can either comment out random cities and then run default cities, or I'll currently still running random cities, which generates 10 cities in the 100 by 100 country that we have. Yeah, so I have printed connected cities over here. This list, what does it actually tell us? So this basically says from city 1, we are connected to city 2, then from city 2 to city 3, city 3 to city 4, and so on. And then again in the end, city 10 to city 1. What I have, I have generated cities randomly and I've connected this path by default. Okay. So now we'll actually move on to simulated annealing. This is the perturbation function that I was talking about. What this basically does, it generates two indexes between these numbers, and then yeah, over here it randomly swaps the coordinates of the cities. As I explained in my case, like it's swapping the coordinates of Mumbai and Chennai as I explained. So this is what happens here. I've just defined the function here. Now we'll start with simulated annealing. Over here, there are many things such as these variables. These are all just to improve your understanding, but you just have to focus. I'll show you the main program. So I've set initial temperature to 200 and I've set alpha as 0.95. What happens is if I multiply alpha with the current temperature, it just makes the temperature reduce by 5% for every iteration. I have at the end of the file, T1 star is equal to alpha. This reduces the temperature by 5%. Yeah. So we have a current distance and object. This is the objective function which we have defined. It gives us the path of the cities present in connected cities. In our case, this is the default. So it gives the path distance to travel through these cities. Yeah. So that is the current distance. I run the program these many times. I update the Turing path. I get the new distance, and then I see if the new distance is less than current distance. This is all the all the algorithm which I've shown you before, and all the other smaller variables are just for like testing to see, like you can like comment out few things, or if you are interested, you can like try to graph them and see how the program runs and all. Over here, I've commented out else because we don't really need this over here. And this is all just to, print and all. Okay, I'll run the random cities function. So I have, oh, sorry. I'll reload this website, please. Okay, yeah. So I'll run the random cities, and this is my initial Turing path, and I'll run simulated annealing. Oh, uh, Okay, yeah. So after running that, we have the initial connected cities. This is the best of the touring path. This is the final touring path. I'll run this plotter function. Uh, okay, how? So this is our country 100 by 100 kilometers. These are the locations of the cities which are randomly generated. Now, after this is our initial touring path of by like which the salesman has initially decided. City one is connected to city two to city three and on. Now the program runs simulated annealing. This is the output after simulated annealing has been run. This is the best possible output that my program has gotten. Obviously, as you can see, this is not a global minima, this is a local minima. This is one of the shortcomings of this algorithm which I've implemented here, which is a very straightforward and simple implementation. This can obviously be optimized. So the reason that we are getting this as the final solution, which is not obviously the best one, is uh, like the program is going through the objective function. It at a higher temperature, it is able to explore various minimas in the objective function. And let's say it reaches some minima, and then while exploring, it reaches some minima, which is not the global minima. And then the temperature is so low that it is not able to actually escape out of the minima. So then only thing it has, only option that it has is to converge to that minima. So in that case, you end up with this not good final solution. Okay, yeah. So I'll come back to the slides. Hmm. Okay, so I have shown you the program. I'll share the program with you as well. You can try it out yourself. Now, what are the advantages of simulated annealing method? Well, in the case of brute force method, you have seen that it has a time complexity of n factorial. What this means is, I mean, it basically is very bad for us as the number of cities increases. The amount of computation it requires scales by n factorial. But then in simulated annealing, the average time complexity is around n raised to power 4. So let's say if you have 100 cities in brute force method, it would take 100 factorial computations. But then in simulated annealing, it will take 100 raised to power 4 computations, which is a very significant improvement. Huh. And disadvantages of simulated annealing is obviously, as you have seen through my code, we were not able to converge to a global minimum. That is just because I've made a simple implementation. I haven't optimized the program. But I mean, obviously you're trying to get a good enough solution, which takes less time and computation power over getting an exact solution. As you would assume, the difference between your current solution and, or I mean, whatever solution you get and the exact solution is not much, and you're having a huge advantage in conserving your time and computation power. Now I would like to compare another algorithm called nearest first algorithm with simulated annealing. Simulated annealing is a physics-inspired algorithm, but nearest first algorithm basically goes as you select your initial city wherever you want, and you travel next to the city which is closest to you. Um, you keep on doing that until you have reached all of your destinations, and then finally you return back to your original city. So I'll run the nearest first algorithm as well, and then I'll compare it with simulated annealing. Okay, yeah, this is the same city location that we had previously. On the same coordinates, I'll be implementing nearest first algorithm. So, okay. So I have in nearest first algorithm, what I've done is I've initially randomly selected a starting city. I've run it first time with city 8 and then next time with city 10. And with each starting city, I go to the city which is nearest to it. So in this case, city 1 is nearest to city 8, then city 9 is nearest to city 1, and so on. So this is the output that we get after, okay, wait, actually. Okay, huh. So this is the output we get. Okay, over here I've started with city 6 and now I've started with city 1. This is, okay, luckily in this case you have gotten similar Turing path. But what happens is sometimes the coordinates of cities can be arranged in such a way such that the nearest first algorithm always gives a worse solution compared to simulated annealing. And also what happens is in certain other cases, in case you start with city 6 and you start with city 1, you may actually have different travel distances. I mean, the travel path that you have is very highly dependent on your initial location. So that is one thing over here. Okay, I'll try to do this again and see if we get a. Uh, okay. Uh, Wait, I'll have to reload this again. Uh, okay, fine. I mean, I'll move on to the advantages or yeah. Okay, yeah. So I'll compare nearest first algorithm and simulated annealing algorithm. And yeah, I would urge you to like run the nearest first algorithm again yourself and try it out. So yeah, computation requirements. So you have obviously seen currently that for the case of 10 cities, nearest first algorithm has actually given us a very good solution. But what happens if you have multiple, let's say 100 or 1,000 cities or locations that you want to visit? The nearest first algorithm also fails in this case as the computation again is increases very at a high larger scale than simulated annealing. And yeah, another thing is nearest first algorithm gives a different path when we start from different starting points. Okay, yeah, so that's it for my topic. If you have any questions, you can ask. What does temp max current do? Does it simply mean how frequently the code will run for exact solution? Okay. What temperature max is? I mean, in the annealing process, initially the metal is heated to a higher temperature. That is the temperature we set as temp max, and then we reduce that temperature by 5% every time till it reaches T minimum. So that is what temp max corresponds to, not how frequently the code would run for execution. But if you set your, like for every iteration, if you reduce your temp max by let's say 2% and then you keep your T minimum very low, I mean very close to zero, then the obviously the program would run for a lot longer than if you set a minimum temperature higher. Yeah, that is that. Any other questions? And I'll hand it over to next presenter. What does temperature exactly relate to code? Okay. Temperature is we are using that to temperature. I mean, we are obviously running. What does temperature relate to? I would say temperature actually simulates the energy present in our path, present in our program. That is, at a higher temperature, you will be able to accept worse solutions. that basically means at a higher temperature, atoms are able to move around more, and then they might like actually travel a farther distance. They have higher velocities. They move around a lot more, and that is what a higher temperature is. What I would say is it is basically the count of energy in our function, energy in our program, and as it reduces, the energy keeps on reducing, and it becomes harder to accept Verser solutions. What this means is, okay, yeah, it becomes harder to accept Verser solutions as the temperature is lower. Atoms do not move around much more. They just move around like in their immediate neighborhood. Like they do not jump around in their crystal lattice. Is that what I would like to say? At a lower temperature, and as the temperature keeps on cooling, all the atoms gradually settle into order. Yeah. So, did you get that then? Okay. Yeah. Yeah. Any more questions, or else I'll hand it over to the next presenter. Okay. I'll send you some notes for that. I'll send you the program and the notes. Okay. Yeah, I'll hand it over to the next presentation.
Hi guys, is my screen visible and am I audible?
Yes, yes.
Okay, fine. So hi, I'm Pranav and I'm going to be explaining the concepts of quantum annealing. And so what is quantum annealing? Does anybody have any idea regarding this? Respond in the chat box. Anyone? Okay, fine. So quantum annealing is sort of similar to what Toshit took. It's similar to simulated annealing. And this algorithm also tries to find the minimum of a given function. But the only difference between this and simulated annealing is while simulated annealing makes use of the traditional and classical algorithms, this makes use of the quantum mechanical principles like quantum tunneling, quantum fluctuations, quantum superposition, and algorithm principles like that. So let me brief you regarding each and every uh, principle which is used in quantum annealing. So let's begin with quantum tunneling. Quantum tunneling is a really interesting phenomenon where particles can pass through potential energy barriers that classical physics would deem impassable due to the insufficient energy. Uh, can you guys guess the reason why these particles are able to pass through these potential energy barriers? Farhan, it's not exactly the uncertainty principle. Yeah, Mudit Tarak, exactly. It's due to the wave nature. So this occurs because particles also exhibit the like behavior described by their wave functions. These waves can extend through and beyond physical barriers, allowing for a small, let's say, a non-zero probability that particles will appear on the other side of the barrier, despite not having enough energy to cross it conventionally. So this concept, it's used in simulated annealing, but besides that, it is also used primarily in making tunnel diodes and scanning tunneling microscopes. Then we'll move on to the next principle which is used, which is quantum fluctuations. So quantum fluctuations, does anybody have any idea what this could be based on? Uh, okay, Ahmed, I'll repeat. So the next concept is quantum fluctuations. Like, do you know what quantum fluctuations? What is the fundamental principle behind quantum fluctuations? Like, what is it based on? Do you guys have any idea regarding that? I think Farhan already answered that previously. Yeah. Okay. So quantum fluctuation is sort of like, teleportation, like what was mentioned. It's like a temporary fluctuation in the amount of energy at a very microscopic scale. Like there's suddenly an empty space, and suddenly there's a blip of energy which comes into existence and then vanishes momentarily. So if you take a look at the GIF, it is an accurate representation of what actually happens in as quantum fluctuation. So then we'll move on to the next successive principle, which is, this is a small question for you. I would like if all of you to respond in the chat box. So guess the successive principle which I'm going to talk about based on the first image, and if possible, identify the movie in which this came. Ahmed, nice. Any, what concept am I going to talk about? Do you have any idea? Okay, what is Schrodinger's cat experiment based on? Malavika, do you have any doubt? Superposition. I can't. Superposition is correct. So let's go ahead and talk about superposition. So quantum superposition is a really fundamental principle in quantum mechanics. It states that all particles can exist in multiple states or positions simultaneously until measured or observed. So similar to what we saw in Schrodinger's experiment, where he puts his cat into a box, and he can't definitively say that the cat is alive or dead until he opens the box. Similar, that is actually the really layman's term of explaining what quantum superposition is. So if we have to put it in a complicated and rather a technical way, a quantum particle's wave function can encompass all the possible states at once, with each state having a specific probability of being observed upon measurement. This concept is really important, and it plays a really important role in understanding the successive concept of quantum entanglement. So does anybody have any idea about quantum entanglement? Have you seen it anywhere, or uh, read about it anywhere, seen it in a movie or something? Electron spin is entangled, yeah, correct. Genius season 1. Yeah, I've not seen it, but I hope you guys have seen the movie The Marvels. Yeah, Marvels is sort of based on the concepts of quantum entanglement. And quantum entanglement is a phenomenon where particles they become interconnected in a way that the state of one particle instantly influences the state of the other. So let's say two electrons are interconnected. So if you determine the spin of a particular electron, then it can indirectly, uh, predict the spin of the other one also, since they're entangled. And uh, it's sort of like an instantaneous form of communication between the two particles. Then now I'm just going, this is the difference between simulated annealing and quantum annealing. So when we take a look at a brief look at the slide, we see that while the mechanism of simulated annealing depends on thermal fluctuations as mentioned by Toshit, quantum annealing rather depends on quantum fluctuations and quantum tunneling. And the efficiency of quantum annealing is rather higher because it can tunnel through the barriers and avoid local minimas more effectively, and efficiently find the global minima and find it in a way quicker way. And the implementation of simulated annealing requires classical algorithms in conventional computers, while quantum annealing it requires some a bit more advanced technology like quantum processors, which are developed by D-Wave Systems, Google, IBM, etc. So this is one of the biggest disadvantage of quantum annealing because of the requirement of these quantum processors which are still under development. Now, the concept of quantum annealing, along with other parallel concepts, paved the way for development of quantum computing, which has the potential to revolutionize the way and approach to solving complex problems. So quantum computing is one of the upcoming concepts which are being explored a lot, and I'll pass it on to Ganesh, who will explain it a bit more in detail. Do you guys have any doubts regarding this? Used in Endgame for time travel. Ant-Man 1 teleportation, yeah, it's sort of connect. Does anybody have any other questions regarding any particular concept? Okay, fine. So, Ganesh, please take over.
Yeah, hello. Am I audible?
Yes, you are.
Okay. Yeah, thanks, Pranav. Mhm. Just a second, I will just share my screen. I hope you can see my screen. Can I just get a quick confirmation? Okay, sure. So, yeah, welcome everyone. A quick introduction. My name is Ganesh. I am a chemical engineering undergraduate here in IIT Madras, and I just completed 2 years here. I really like math, and I hope I teach you something here uh, that will ease things up for you when you want to actually explore quantum computing. So, what is quantum computing? Uh, it is so throughout uh, Pranav. Okay. So, as the theme of the of the summer school goes. We are looking at different ways to perform computation inspired by physics. So we have looked at different algorithms. Srijan, Pranav, Toshit have gone over different algorithms, and quantum computing is actually bigger than that. It encompasses more. It encompasses more things than those algorithms because quantum physics in itself is a very huge part of physics. And yes, so since we have very less time, uh, I'll try to capture as many things as possible so that it will get you started when you want to go ahead and look for things to read more on quantum computing. So yeah, first things first, let us understand some basic quantum physics. I'll just quickly go through it. I'm pretty sure most of you people here are either high schoolers or uh, in the first year of the college. So this should be pretty familiar. It will be a brush up if you're already familiar with it. So a quick overview. So there are some four phenomena here, and I'll just quickly go through each. So I think this is pretty standard. I think many of you have seen it, and this picture itself I have taken this from Feynman's lectures. So it's from Feynman's lectures volume 3. So if you're interested, you can go and read further as well. I'll quickly try to brief whatever he has tried to explain. So you have a gun here, a machine gun which just sprays bullets. You have a screen which with two slits, and then you have a screen far away which just absorbs and detects where the bullets fall. So what I'll do is I'll block the second slit. I'll just open the first slit and then I'll fire a ton of bullets. And we notice that the bullets form this kind of a probability distribution P1. So around this area, the probability of the bullet falling is higher than the other regions. Similarly, if I close slit 1 and open slit 2, I'll get a similar probability distribution P2. Now, basic math and intuition says when I open both slits, the probabilities should just add up. And yes, it does. So when I open both the slits, it's the same as adding the total probability is the same as adding the individual ones. And only one was open. And similarly, we can do this for waves as well. Like we did for particles, we can do this for waves. And in waves, instead of trying to measure if a particle has hit or not, if if a particular point in screen, you have detected a particle or not, you use something, you measure something called the intensity, which is just the amplitude square. I'm pretty sure most of you are familiar with it. If not, just let me know. I will try to say that again. And yeah, feel free to interrupt anytime. If I don't see the chat, and open your mic and talk as well. So yeah, we know that the intensities do not add up simply. They form kind of this wavy pattern with maximum and minimums. And this is because it's due to the phase difference between them. That's why they don't add up like we expect them to. They add up with some angle. So you have constructive interference at some point and destructive at some other points, and you get kind of this wavy total distribution. Now, the interesting part is what happens to the distribution when you fire a particle, but the particle is really small. So here is a very similar gun, but this fires electrons instead of bullets. And if you notice again, we have a similar probabilities, individual probabilities P1 and P2. And again, intuition suggests that probability should just simply add up. But here it doesn't. It doesn't add up the normal way we think it would. It adds up the way the waves would add up, the wave intensities would add up. So this is kind of weird. We don't really expect this to happen because it's not like half an electron is going from the one slot and the other half is going to the other slot. Electrons can't split. They are solid chunks. That's what we think. So that's clearly not what is happening, and we'll try to shine a light in between and see what exactly is going on. And if I just keep a light source in between and try to observe what exactly is happening between the region, I immediately get a different probability distribution. So this now behaves just like you would expect a normal particle to behave. So what has happened here? The same event, but due to the very fact that you're observing, the event outcome changes. So this is exactly what the Heisenberg uncertainty principle is. I'm pretty sure most of you are aware of it. It just says when you try to observe something, to be more precise, when you have a light source, it affects it hits the electron and it changes the momentum of the electron. So it's no longer the same event that you're observing. So in these two cases, that is the difference. So this experiment in essence was the founding or the big question in quantum physics. That's what started everything. And this uncertainty principle is something that helped explain what was going on, why this observing gave us a different result than what actually happened. And, yeah. So again, quantum computing is it's a very theoretical thing, so a territory. So as unlike other computing, uh, as well like in the normal computing, have a lot of practical things to do, but quantum computing is still just pie in the sky. So you have a lot of theoretical rigorousness to have, and for that you need math. Uh, the math that you need here is just some basic linear algebra. I'll try to quickly go through the necessary things that we need to actually get started. It's time for some linear algebra. So these are the things that I would like to discuss. So I think this should be necessary for what is coming next. And this is something that you will study in your first year in introductory math courses. If not, fine. I will just try to explain it from the scratch again. So what is a vector space? A vector space is just a collection of vectors which satisfy some properties. It's just a set of vectors, but we impose some certain properties, some certain conditions on them. So instead of just trying to randomly collect a bunch of vectors, we collect a bunch of vectors in such a way that they obey these properties. Why do we do that? Well, if we impose these properties, we can get some nice results out of them. So some of these properties are you say that you always have to include the zero vector in your vector space, so your collection of vectors, which is a vector space, and you impose a condition that the vectors are associated. You say that the vectors are commutative, the addition is commutative, and stuff like that. So when you do that, you get some nice results out of it. And so when you just collect a bunch of vectors, anything can happen. So we don't want that. We restrict ourselves to some certain properties so that we can get some useful results out of them. Yes. So uh, till now, most of us think of vectors as just pointy arrows in the 3D space or in some R to the N space. But it can be more than just a bunch of numbers. Some functions can also be vectors. So what do I mean by that? So let's just take this simple polynomial x square plus 2x plus 1. You can represent this as a vector by just simply denoting it as 1, 2, and 1. So when I first say add two polynomials, x square plus 2x plus 1, if I add it with x square plus 3x plus 2, it is the same as adding 1, 2, 1 column vector to 1, 3, 2. So when you add polynomials, in essence, you're just performing vector addition. Okay. That is the way to think about it. And so some more examples are if some of you are aware, Fourier series is just it's rewriting your functions in a different basis and in an orthogonal basis. Your sines and if you treat your sines and cosines as vectors, you just try to map them to a different vector space. That's what essentially Fourier series is. And if you have done some magnetism and stuff, you would have come across Legendre polynomials. They're just another basis for polynomials, or another vector space that is span. So when you think, when you generalize vectors, you can fit much more things like functions into it, and you can describe the vector properties, which make them really easy to work with. So that's the reason we abstract away from just thinking of vectors as just a list of numbers or some point in some space. And some generalization further would be, having infinite dimensions in a vector. So that's what mathematicians do. They try to abstract it to the absolute maximum. But I don't think that will be relevant for us, at least not right now. Yeah, and so we define something called a vector space. Now we'll define something called a dual space to the vector space. So if you have a vector space V, which is again just a bunch of vectors, the vectors in the vector space V star, the dual space, are just vectors that map or just elements that map these elements in V to some scalars. So a scalar or a scalar is something you use to define define a vector space. When you define a vector space, you naturally define something called a field with it. A field is nothing but it can be a real number, it can be a complex number. But what I'm essentially saying is when you first multiply a vector 2 comma 1 with 2 with a factor of 2, that 2 is actually a real number. That you call it a scalar. You can multiply the vector with a complex number, for say I 2 I times 2 comma 3. So this field is a scalar that we are talking about. So when we have some column vectors as vectors in our V, we'll naturally have row vectors in our dual space. So that when you kind of multiply these two row and column vectors, you get a number. I think this is what we call dot product. So the 1, 2, 3, we have the row vector 1, 2, 3, and we had some column vector here 0, 1, 1. You can just take the dot product, and that will just give you a real number or a scalar. So that the row vector space would be the dual space for your column vector space. I hope that makes sense. Yeah. And yeah, so inner product is just again a generalization of the dot product. So a dot product is typically defined for a Euclidean space. When you have a real vector space over real numbers. But you can do it with complex numbers as well. So that's where we try to generalize the dot product to this inner product. There's a famous saying in real analysis, the study of real numbers is incomplete without complex numbers. So there is a reason we try to generalize these things. These come out to be very useful later on when we try to prove something. Yeah, so the inner product is very similar to a dot product. So the inner product is just represented by this angular braces. So the inner product of A and B is just a B star times A. It's not B times A, it's B star times A. B star is nothing but the conjugate transpose of B. So when your A and B are vectors with real entries, B star is just the B transpose. But if the entries are complex, you should take the conjugate as well. So B star would mean the conjugate transpose of B. So that is roughly the generalization of the dot product. And norm is again the square root of the inner product of a vector with itself. So this is kind of your magnitude in your Euclidean space. Hope that makes sense. Okay. Yeah. Now comes something many of us would have not heard about. So what is a Hilbert space? Well, this is a question Hilbert himself asked. So yeah, here's a quick funny anecdote. I'll just give you a minute to read it. Okay. I hope you guys read it. So, I mean, Hilbert was a German mathematician, so this is kind of like the English translation. And yeah, so Hilbert himself didn't know what the Hilbert space was. So I think we are pretty close to Hilbert in that sense. But again, but the real definition of Hilbert space is just a complete inner product space. So there are two new terms here. So I think now we are in a position to define these new terms in terms of whatever we just defined. So an inner product space is nothing but a vector space with a definition of an inner product. So if the inner product definition I gave here it's very rough. There are some additional conditions for this inner product to make sense. Or something like the inner product of A and B is the same as a conjugate of inner product of B and A. So there are some other conditions, and if the conditions are followed and the inner product is defined, you can attach it to a vector space and call it the inner product space. So inner product space is nothing but a vector space with this inner product definition. So what is a complete inner product space? Complete space means inner product. If you look at the actual mathematical definition, it says all norms converge to all Cauchy sequences converge something along those lines. All Cauchy sequences converge, but I think it's for now we'll just take it as an inner Hilbert space as an inner product space where all the metrics are defined. So a quick example of a complete inner product space would be when when you have 2 points at infinity. So when you are at the x-axis, when you're along the x-axis and you go to infinity, and you just say you have 2 points at infinity. When you subtract them, when you find the distance between them, you just in your norm, when you try to define that with your norm metric, it should come out to be 0. That is what the Cauchy sequence means. So there are some other inner product definitions where though they might not be equal to 0. If A goes to infinity and B goes to infinity, we just say B minus A is 0. But there are some definitions where B minus A will not be 0. So that will be an incomplete inner product space. So Hilbert space is kind of nice. It is complete, and it is also the usual real world spaces that we have. Our usual real world spaces are also Hilbert spaces. And yeah, so final thing in math. So I think this is the last thing before we get into the actual physics. So this is it's called the Dirac notation or the bracket notation. It might seem scary, but it's just, if you look at it, it's just very convenient. So a ket is just a vector denoted with a bar on the left side and an angular brace on the right. And a bra is something, it's a dual vector to that ket vector. It's defined with a left arrow and a bar at the right. So it's convenient because when you try to take the inner product, you just kind of try to match the two bars together. So the bracket is just the inner product. So you represent it by just merging those two bars together. And there's something called the tensor product as well. It's when you multiply two kets together. And yeah, I think that will equip us enough to actually go to the quantum part again. I will just pause for a minute. If any question, you can start. Okay, I don't think there are any questions. Oh, just so I know you guys are here, just give me a thumbs up so that I know you are actually listening and not, away on something else. Okay, that's nice. Yeah. Okay, so I'm connected to you people. I'm audible. Yeah. Yeah. So here comes the interesting part. So you might have learned about angular momentum. So an angular momentum. So I'll just we are actually running out of time, so I'll try to finish this up quickly. So angular momentum of an electron is quantized. So it's either plus h bar by 2 or minus h bar by 2. H bar is that Planck constant divided by 2 pi. So the spins, so it's either top spin or bottom spin. There are two quantized spins. this has been proven experimentally through an experiment called the Stern-Gerlach experiment. So there is a video for this. I will just quickly show that. Yes, I hope you can see the video. I just play it. There's no audio. Yes, that's it. So in essence, okay, there's a question here. I'll just try to answer that quickly. Is psi defined? So just a second. I hope you can see my screen again. So the thing is psi and a psi defined. So you're trying to say trying to multiply a bra by a bra. So that is defined. You can that's again would be some sort of a tensor product. It's kind of like trying to multiply 3 cross 1, 1 cross 3 vector with a 1 cross 3 vector. So in a usual sense, it doesn't make sense because their dimensions don't match. But we can multiply them in the tensor way. That is possible. Okay, so coming back to this, yeah. So the essence of this experiment is there's this fun idea that people came up with. So what it says is, I have this source of some electrons. I have some neutral atom. I'll fire some electrons, and I have this SG filter. So this is kind of what we saw in the video. That filters out electrons based on the spin in a particular axis. So they have these spins along all three axes. So along particular axis, Z axis, I will separate them like we did in that video. So and one stream, half of it will be in a neutral atom. Approximately half of them will be plus half spin, and the other half will be in the negative spin. And I take the positive spin ones alone, and then I'll pass it through another again another Z-axis filter. What you see is kind of intuitive. You again only see only the positive half, the positive spin electrons coming out. So this experiment makes sense. Similarly, we try to do again with a slightly different setup. First, we'll filter out the Z spins, and then we'll filter out the X spins. So after filtering out Z spin, we take the positive spins and then we filter it out again along the X-axis. We again get what we kind of expect. So we get the X-axis separation. Half of them will be positive spin along X-axis and half of them will be negative spin along X-axis. So here comes the interesting part. You have this setup where you first filter it along the Z-axis, the spin along Z-axis. You send that filtered part through an X-axis filter, and then you again send the X-axis filtered part through Z-axis filter. So what do you think will happen? So do you think you will get only the Z half, Z positive electrons or Z negative electrons, or do we get both? Anyone? Okay, so I hope the question was clear. So these boxes filter out the electrons along a particular, based on the spin along a particular axis. So the first one filtered it along Z axis, so it filtered it into positive spins and negative spins. We are taking the Z positive spin electrons to another x-axis filter, another filter. Now it filters it along the x-axis. So now we have the positive the positive spin along x-axis electrons. Now you again pass it through the z-axis filter. So we, based on our previous experiments, we again expect it to come out as the z positive only, because we already filtered it out here in the first step. But if you actually look at the result, you get both z positive and z negative. So you get both uh, positive Z spin electrons and the negative Z spin electrons. So that is kind of interesting. We would never expect that because we already filtered it out somehow in the uh, first box. But okay, someone asked how. So that is exactly the point of confusion. That's how quantum systems behave. So this we'll try to explain it with math. So we'll try to create a certain certain definition, certain set of rules so that this makes sense. And in fact, we can come up with a way. So here's some very big notation. So I'll just break it down. So this zero is just it's like a ket vector you've seen there. It's a column vector. So this 1 0, it's kind of like your I hat. Uh, but I can't say I had here because we are going to use complex numbers as well. So I and J are both out of the question. So we'll use this notation. So 0 will mean 1 0 column vector, and this one notation means 0 1 column vector. Kind of like your x-axis and y-axis. So let these two vectors uh, denote the z spin. So if your z spin is positive, let it be 0. And if your z spin is negative, let it be 1. So I'm just kind of defining it to be orthogonal vectors. In fact, orthonormal. And based on that, if I try to define the y spins as the vector, along 45 degrees. So kind of like in your Euclidean space, it would be I comma j by I plus j by root 2 and minus I plus j by root 2. So if I denote the basis vectors for that, the y spins in such a way and x spins in a complex way. So uh, so I define z x spins to be 0 plus I times 1 by root 2 and 0 minus I times 1 divided by root 2. So and with all this definition, I define this black box to be kind of like an inner product. So why does this definition make sense? So this definition together, if you recall, this forms a Hilbert space. So if you go back, for say you go back to the first experiment, so you send source which contains a random state of all these spins. So sending it through a filter is like trying to find the inner product with the Z components. So your Z components were recall 0 and 1. So it's kind of like taking the dot product or the inner product with this 1 0 column vector. And if you see this, they are both symmetric. So any vector you take, the inner product will be the inner product with 0 and 1 will be equal. So that's why you kind of get like a 50-50 probability. And right, yeah, 50-50 probability. And again, you take the inner product with 1 or 0. I think positive you can define it to be 0 and z minus you can define it to be 1. So taking the inner product with, so essentially the SG filter box is like an inner product. If we define it that way, this experiment actually comes out making sense. So let us say I'm sending a source with Z1. So Z negative, let it be denoted by 1. So I'm sending it here. It everything, there will be no Z minus, everything goes to Z plus. And now I'm sending it through x-axis filter. So if you go with the definition of this box, so the inner product. So if you take the inner product of 0 and the x-axis was defined as 0 plus I by root 2, 0 plus I times 1 by root 2. If you take the inner product with that, you actually get both the z components back. You'll get two components both in your resultant vector. So in this framework, if you define the electron spins to be an element of the Hilbert space, this actual quantum behavior can be explained. So we don't know why this happens, but we can explain that if it happens this way, we are able to figure out that this math makes sense. So this is kind of how we think this works. Yeah, it's actually crazy stuff. So, yeah. Again, I think I have this has been a bit hand wavy. So for a proper definition, I think we will need put in more time into this so that you understand. But the intuition is that. So the intuition is that this eventually works out, and the electron spins come out to be an element of the Hilbert space. So that is pretty cool stuff. And okay, let's we are really running out of time, so let's just try to get this over with quickly. So I think many of you have heard about qubits. A qubit is just, you have a classical bit. In your classical bit, you have zeros and ones. It's a binary. So it's either 0 or it is 1. But in a qubit, it can mean a superposition of 0 and 1. I think even Pranav, I think went through asked you briefly about this. So I think most of you are aware of what superposition is. So yeah, why did we do all this? Why did we define all this? Why did we consider the spin electron system? Because as it turns out, this is a qubit. You can define it to be a qubit because the any state, any spin state the electron is going to be, the bunch of electrons going to be in, is just going to be a combination of the zeros and one. In a sense, it's a superposition. So a spin half system can be it is technically a qubit. So what can you do with it? Okay, so this is typically how a qubit is represented. So this is kind of, if you recall, it was exactly like the definitions here, the electron spins. So it's 0 plus something, 1 by root 2 times 0 plus 1 by root 2 times 1, and 1 by root minus 1 by root 2 times 0 plus 1 by root 2 times 1. So this is a general way of defining it. So this gamma is just a phase factor. When you take modulus, it's going to vanish. So let's not worry about the phase factor. We have two other parameters here. So you have theta and you have phi. So when you vary theta and phi, you obtain different possible states of that electron, of the spin of that electron. So you have two parameters here, and this can be viewed or try to be made visual with something called the Bloch sphere. So if you guys attended the first session, this picture was actually there in the intro page. So that is actually the Bloch sphere. And again, a fair warning, this might confuse you because if you see, if you have noticed earlier, we have defined 0 and 1 to be orthogonal vectors. We have defined 0 to be 1 comma 0 and 1 to be 0 comma 1, but here they lie on opposite sides. So the reason is this does not follow your Euclidean metric. This is a completely different way of looking at it. What it says is you have 0 on the north pole, 1 on the south pole, and if you just vary theta and phi, you get these different points on the sphere. And these each point on the sphere is uh, a particular state of the electron. So you would intuitively expect it to be a circle, but because we're dealing with complex numbers, you have this extra dimension. So if you only dealt with real numbers, you would have had just a circle which goes around 0 and 1, around the north and south pole. But since you're dealing with complex numbers as well, it turns out to be a sphere, and the sphere is called the Bloch sphere. It's a nice way to visualize. So I'll give an example as well. So how it is useful in visualizing. Okay, so let's come to gates. So we have we are all familiar with gates in classical computing. We have AND gate, NOR gate, XOR, or plenty of them, and it can define something similar for this quantum qubits as well, quantum bits, and yeah. So a gate can operate either on a single qubit or it can act on multiple qubits, just like your NOT gate acts on a single bit, and your OR gate needs 2 bits to work out. So they are unary and binary operators. So if you per se consider unary gate in qubits in the quantum realm, you can actually model them to be a matrix, a 2x2 matrix. So the only condition is that 2x2 matrix has to be unitary. Oh, oops. Yeah. So it has to be unitary because unitary matrix is nothing but for say if your matrix is U, so U transpose U's identity. So that is when you call the matrix U unitary. That condition is there because it respects the norm definition in the new space as well. So a NOT gate or an X gate is simply this a 2x2 minus 0, 1, 1, 0. And if you operate it with any qubit, so 0, 1 is a possible, this is actually a 1, the negative Z cube spin. If you operate on that, you get a positive spin. So yes, so x of this alpha 0 plus beta 1 is equal to beta times 0 plus alpha times 1. So we kind of swap it. It's exactly not gate. And yeah, the alpha and beta here are some numbers, but alpha square plus beta square has to be 1 because the ranges, the values can be between 0 and 1. They cannot go beyond them. So alphas and betas have that constraint. So why do we call this an X gate? Oh, is there a reason? Yes, there's a reason. This is called an X gate because if you look at the Bloch sphere and see this operation, it's just equivalent to rotating the state vector by 180 degrees. So that is why it is called the X gate. So if you look at the diagram here, so if you have your vector here, if you have your vector at state vector at 0, your NOT will be just mapping it to 1. So that will be just a 180-degree turn along the x-axis. So a point here will just go diametrically opposite here. So it rotates it above the x-axis, and that's precisely why it is called the X gate. Okay, so I think it's the right time to end the end the session. So this has been the basics. So we have discussed some math. We have discussed some basics of quantum computing, what qubits are, what electron spins are, the Dirac notation and stuff like that. So this should be enough to get you started with quantum computing if you want to learn more. So some possible avenues there are some keywords that you want to look for if you're going to study more. So we have only discussed about single qubits, but there can be multiple qubits as well. So when you have multiple qubits, the entanglement factor also comes in. I think Pranav talked about it. So the entanglement is nothing but if you see it purely in a mathematical way, it just turns out to be the tensor product that I mentioned a couple of slides ago. It's just the ket times the ket. So it's kind of like that. So the entanglement is also, understood by math. So that's a real fun part. Everything here is just rigorously proven with math. We just don't have enough, resources or enough knowledge to actually implement it as of now. So quantum computing is still something very theoretical, and yeah, so at least the math works out. That is a good part, and we'll keep looking forward to any advancements, I guess. And yeah, there are some quantum analogs of classical algorithms. You have the search algorithms, you have the sorting algorithms, and they can be done with qubits or in the quantum way in much faster. So if your normal classical algorithm takes for say is O of n time complexity, you can probably get some O of root n time complexity in when you do it with qubits. So there are some algorithms, there are some basic algorithms. So something called the Deutsch algorithm. There's something called the Grover search algorithm. So you can probably look, search them up and try to understand. And yeah, there's so much more to read about this. And hopefully this was a good starter to whatever you will try to read. And I hope that that won't be scary to read anymore. So yeah, that was it. If you have any questions, you can ask. Otherwise, I think we are done.